Alright, so what we're going to do in section 1 is start looking at integrals and how they work. And what integrals do is they add up the area under a curve, between a curve and the x-axis. And the basic part of that is just looking at specific shapes under the curve and just kind of looking at how all of this occurs. So what we want to do is, without getting into a lot of calculus right now, we're just going to estimate the area of a rectangle. We're going to use the area of a rectangle to estimate the area under the curve. And what we've got here is a question, finding the distance traveled when the velocity varies. In other words, the velocity is constantly changing. So they give us a velocity function of t squared for time where t is greater than 0, where's the particle when t is equal to 3. And so the first thing that we want to do is find out, okay, where exactly are we when t is equal to 3? So we're going to look at our velocity equation, and we're going to say that v of 3, and that's going to be equal to 3 squared, which is 9. So on our graph that I've got for us, we're just going to look over here, and we're going to start at 3. So here's 1, here's 2, here's 3. And we're going to just look straight up here like this, and we're going to find the area under that curve. Oops. All right, so let's get this guy straightened up here. Okay, so what we're going to do with this guy is we're going to look at the area, and we're going to look at the area specifically in this spot right under here. And we're going to stop it at 3. Okay, well, this is a curvy thing, and so until we get into the calculus part of this, finding the area of a curvy thing, all we're going to be able to do is estimate that. And so what we're going to do is we're going to find the area using what's called subintervals. We're going to partition or split apart or separate into 4 subintervals this graph. And to do that, we're going to go from 0 to 3. And so if we're going to use 4 subintervals, we would say that n equals 4. Okay? And the distance that we're looking for this area goes from 0 to 3. So to find the area, you're going to do your stop minus your start for your x-coordinates and divide it by the number of subintervals or partitions that we want to make. So each subinterval is 3/4 of a unit wide. Now this is where it gets really interesting. So what we're going to do is we're going to come out to 3/4, and then we're going to come out to another 3/4, and that's going to put us at 1.5. Then we're going to come out to another 3/4, which is going to put us at 2 1/4, and then we're going to come out another 3/4, and that's going to put us right at 3. And what we're going to do is find the area of a rectangle that's inside each of these subintervals. And what we're going to do is we're going to take this left-hand side right here, touch the curve, and we're going to make a rectangle. So my first rectangle, which would be at 0 here, he touches the curve at 0. So my first rectangle is actually flat, so there's nothing there. And then my rectangles are going to look like this. And oh, whoops, that needs to be a little bit further over. Needs to go over to here. So here's my 4 subintervals. Now you'll notice when we take the area of these rectangles that I'm going to be a little bit short of the actual area of the curve, but this is going to be an approximation, and so that's okay. So what do you get? Well, we're going to find the width, okay, because remember the area of the rectangle is length times width, and so the width of each of these rectangles is 3/4. So for this particular problem, our width is going to be 3/4. And then the height of each rectangle, or the length, or whatever you want to call it, is going to be the function at those different partitions, at those different subintervals. So I'm going to have 3/4 squared would be the height of this first rectangle right here. Actually, the second rectangle. So what would the area be? It would be 3/4 times 9/16. Okay. Well, what about the next guy? So we're going to take 3/4 again. So this guy's going to be 3/4 here, and his width right here is 9/16. Okay. So that's, and I don't want you to think it's this third rectangle. It isn't. It's this little short rectangle right here. Okay. Put it on this side and draw an arrow. How about that? So this height right here is 9/16. Okay. Now we want to find this height right here. Well, that occurs at 1.5, or 3/2, we could say. So I've got my width, which again, this width is 3/4, and the function evaluated at that point there. So we would have 3/4. It would be the function v at 3/2, which is the same thing as 1.5, and so that would be 3/2 squared is 9/4. So what we're going to end up with is 3/4 times 9/4. Okay. And so this is going to be this from 9/16 now to 9/4. That's this guy right here. And then we go for the third rectangle, which it's also 3/4 wide, but we need this guy right here. So that's going to be at the point 2 1/4. And so if you're 2 1/4, you're going to be at 9/4. Okay. And so that's going to be the velocity at 9/4, which is 9/4 squared. So let's move these guys again. So this is going to be 3/4 wide plus, or times 81/16. Okay. And what we'll do is we'll add up all of these rectangles areas. And so when we add up all these rectangular areas, we're going to end up with an estimate of the area under the curve. Now it's a little bit short. It's not a great estimate, but it is a good estimate. So we would just add all these guys up. And you might want your calculator to do that. You can do that right now if you would like. And let's see if you match what I get. All right, so working it out with my math, using my calculator, I got 5.90625. And so this would be the area under the curve. And we would say that this is an approximation. It's a rough guess, but it's not 100% accurate. Okay, it leaves a little room. In other, it leaves this much room here, it leaves this much room here, and it leaves this much room here, and it leaves this little slice in here. So it's a close estimate. It's not exact. We can be more precise by increasing the number of rectangles. And so let's do that. Again, let's look at 8 subintervals now. So if we let n equal 8, so if we go n equals 8, then we would do our start minus our stop, which would be, we're stopping at 3, we started at 0, and divide by the number of partitions or subintervals. So each interval is going to be 3/8 of a unit. And this is going to be the width of my rectangle. Okay, this will be the width of the rectangle. So to find the area under the curve, we're going to look at 3/8. Well, we'll look at 0, 3/8, and then add 3/8 to that, all the way up to 3. So 3/8 would be 6/8. 3/8 to that would be 9/8. So here's just over 1. 3/8 to that is 12/8. 3/8 to that is 15/8. And then 3/8 to this would be 18/8. 3/8 to that would be, I don't know why I wrote equals here. Let's get that out of the way. That should be a comma. 21/8. And then 3/8 to that is 24/8. So 24/8, that would be this part of the curve right here, because 24 divided by 8 is 3. So since it's this part of the curve, we're actually not going to use this very last guy. Now, each width is 3/8. Now we have to find the height at those places. Well, we're using the same exact function again. So basically what we're looking at is, let's get this back to green. What we're looking at then is v of t squared. And so our t are all these different widths that we just wrote down. These are all our t's right here. All of these guys are all the t's that we're interested in. Okay? And so what we're going to have is, let's see, I didn't write this correctly. T squared. There we go. So what we're going to have then at all these different widths is just basically a squaring of the numbers that we just found. Okay? So we're going to end up with 3/8 times 0 squared plus 3/8 times 3/8 squared plus 3/8 times 6/8 squared. And we're going to do this the whole way through the interval from 0 to 3. We're just going to add up until we get to that 21/8. So 6/8 and then 9/8 squared, and then 3/8 times 12/8 squared, and then 3/8 times 15/8 squared, and then 3/8 times 18/8 squared, and then 3/8 times 21/8 squared. Okay, now real quick, notice, and this might make it easier on you also when you're doing your math. Notice that we've got a 3/8 in each piece. Okay, we've got 3/8 in each piece. So one of the little tricks that we can do is to make it less to punch into your calculator, because you'll want to do that just to double check yourself. But one of the things that we can do is factor that 3/8 out. And so then we're just left with 0 squared plus 9/64 plus 36/64 plus 81/64. And so it's just a little bit easier to actually punch into your calculator. Let's see, 144, and then 15 is 225, and then 18 is 3, what is 18? So it's going to be a 4, carry 6, 144 plus 18 is 324, and then 21 squared. So it's going to be 21 and 42, so 441. And we would add all those guys up and multiply by 3/8. Okay, so go ahead and do that right now and see if you get what I get. So on this guy, I ended up getting 7.3828, which is closer than 5.96, but still less than where I need to be. All right. So I've shown you a couple ways. Now I left you a doozy to do on your own. You try this guy out right here. See if you can do this one, 12 subintervals, and I'll get you started. So if we're going to have n equals 12, okay, and we're going to stop at 3 and start at 0, then I'm looking at partitions that are a quarter, 1/4 inch or 1/4 units wide. So can you come up with the rest of that, guy? I'll give you, go ahead and pause your notes and do your math, and I'll give you the answer. All right, I got 7.90625. So notice that we're starting to kind of slow down and approach a specific number. We started off with that very first partition. We started off 5.90625. That's 4 subintervals. Then we doubled that and went to 8. And when we did 8 subintervals, we got to 7.3828. And then we went to 12, we got 7.9. So the more subintervals we put in, the more accurate that we're going to be. And the whole thing with the integral, what we're eventually going to do is we're going to look at an infinite number of subintervals. And that's going to be really interesting, but that's not for today. Okay, what we're going to look at now is called rectangular approximation method, or RAM, okay? And this is how the integral is going to work. And there's basically 3 kinds of RAM. There's left rectangular approximation method, which is LRAM. L would be the left. Okay, left rectangular. This would be right rectangular, R for right. And MRAM is going to be the midpoint. Okay, or middle. And so when you're doing RRAM is going to find a rectangle that just touches the curve. LRAM is going to find a rectangle which just touches the curve on the left-hand side. And so you can see on my rectangle right here, right on that very left-hand side of the rectangle, right in there, but you can't see yellow. I don't know why I just picked that. So this would be LRAM. Okay, we're going to make rectangles that touch the curve with that upper left-hand corner. Guess what RRAM does? RRAM takes that same rectangle, but now instead of touching the left-hand corner, it touches the right-hand corner. So what's going to happen is I'm going to have a curve, and remember we did, let me lock this guy. We did LRAM for our first example. What we're going to do on this guy is look at all the different ones. So this is going to be RRAM. Well, RRAM is going to take that same rectangle, but except now what it's going to do is it's going to move that rectangle over, so now that the rectangle's height is on the right, okay, and that's going to determine the height of the rectangle instead of the left. And then the last one is that MRAM, which is your midpoint. So what we're going to do is we're going to take that same spot now and we're going to put the middle of the rectangle and look at the area of the rectangle. Now, notice that with my left rectangle, when I go left, I'm a little bit below my curve. I'm going to have some area of space. I'm going to be an underestimate. When I go with RRAM, I'm going to be an area over the curve. I'm going to have a little bit too much space. And then if I go MRAM, I might not be exact, but I'm going to be right in the middle. So that's, those are the 3 different ways to look at this. So what we're going to do is we're going to take this x squared guy, which we've looked at once already, and we're going to divide into 5 subintervals or 5 partitions. And let's see what this looks like. So let's get rid of these 2 guys. And let's look at these rectangles, 5 rectangles. So what do we want to do? Remember, we're going to say that n is equal to 5. And we're going to start at 0. Boy, howdy. We're going to start at 3. Start at 0, stop at 3. There we go. Start at 0, stop at 3. So stop minus start divided by the number of partitions. So this is going to be 3/5. So every 3/5 of a unit, we're going to have a partition all the way up to 3. So my 3 is right here. So let's real quick do that, guys, so we can see where we're going to stop. And then let's look at 3/5. So we're going to divide into 5. So 3/5 here. And let's see, 3/5 would be about, let's see, from here to here. And let me grab these two guys, and we'll see if we can't. We'll clone them, and we'll try and get as perfect a split as we can here. So here's another one, and we'll clone that. We're going to be really close. Here's another one. We'll clone that. And here's my last one, which is oh so close. All right. Not bad. Not bad for eyeballing it. So these are going to be the rectangles. All right. So if I do LRAM, my rectangles look like this. Notice that the left side of the rectangle is touching the curve. Okay? All right. So what are the different heights? Well, for my LRAM, I'm going to be interested in 0. I want to be interested in 3/5. I want to be interested in 8/5. I'm going to be interested in 11/5. I want to be interested in 14/5. Let's see, 3. Whoa, I did bad. That's terrible math. Holy smokes. This should be 6/5. 3/5, 6/5, 9/5. There we go. Here we go. 12/5. Okay, those are the rectangles that we're going to be interested in when we do LRAM. And we'll take the exact same steps that we took on our first example. Now, what we're going to do is we're going to look at RRAM now. So these rectangles then are going to all slide over. These rectangles are going to slide over now to where the right sides are going to touch. We don't want the actual line though. He needs to stay where he was. Okay. And so we need to add one more rectangle to get to that RRAM. So let's get these guys lined up just a little bit better here. Right sides. Well, I didn't quite catch them all, did I? So get those right-sided triangles touching, rectangles touching. And you'll see that we need one more rectangle now to complete this guy because we've got to go all the way up to the right side. So we're just going to fill that guy in. He's going to go all the way up, right side, which is going to be all the way up to 3 now. And he comes straight out. And notice with the right area, on this particular part of the curve, notice we're going to have an overestimate. Okay, we're going to be too big. But that's okay. So what specific spots are we looking at now? Well, now we're looking at 3/5, not 3/4, holy smokes. 3/5, and we're looking at 6/5, and we're looking at 9/5, we're looking at 12/5, and we're looking at 15/5. All right. And this should be 5, not 15. And so that's going to be my right rectangular area approximation. And remember, on all of these, the width is going to be 3/5. So that's the base of my rectangle. And then on my middle point, we're going to be right in the middle of these different partitions. And so we're just going to slide all these guys over. Let's grab this last guy here. And so we're going to slide all these guys over till we're right in the middle of the midpoint, It should be somewhere right around in here, it looks like. Well, how do you find the middle of the partition that you've chosen? Well, our partitions are 3/5 of a unit wide. So to find the middle of that very first partition, I want to go ahead and divide that guy by 2. Okay? And when I do that, I get 3/10. So for this particular guy, this is going to be 3/10 is my first one. So right over here, really close to 0. Right here, actually. Okay, so I'm going to be 3/10, and then remember that it's going to be at the middle of every interval after that, or 3/5 of a unit later. So I'm going to start at 3/10, and then I'm going to add 3/5 to that. So 3/10 plus 3/5 is 9/10. And then 3/5 to that it's 3/2. And then 3/5 to that is 21/10. And then 3/5 to that (27/10). And so that gives me my 5 subintervals right there. And then we're just going to do what we did earlier, which is we're just going to take that width of 3/5 and multiply it with all those heights added up. And remember, you're squaring those numbers because we're looking at the function x squared for this, or I guess our function was velocity over time. So these are all the times that we're interested in. So 9/25, 36/25, 81/25, 144/25, and then down here the same thing again, except now we're going to lose 0 and we're going to add the 15 squared part. So down here we would have 3/5 times 9/25, 36/25, 81/25, 144/25, and 225/25. And then our very last guy, we're going to take that 3/5, and this time it's a whole different slew of numbers, okay? So because we're going to we're squaring different things. So this is going to be 9/100 plus 81/100 plus 9/4 plus 21 squared, which I've forgotten, 441/100, and then 27 squared over 100, 729. Okay, so we want to find what the areas of each of these guys are. Go ahead and pause your notes right now, plug all this into your calculator, and see what you come up with, and let's see if we match. Okay, so here's what I got. I got, when we did with left rectangular, I got 6.48. For right rectangular, I got 11.88. And you'll notice that these two guys are way different. And remember, one is an underestimate for this particular curve, and one is an overestimate. And then the other one that's probably really, really close is this guy right here, 8.91, and he's the midpoint rectangular area approximation. And the midpoint one is actually the best one to use, the MRAM. It gives you the most accurate measurement, because if we look at the integral of this and we evaluate it analytically, we're going to find that the integral from 0 to 3 of x squared dx is equal to 9. And we're going to learn how to do this, but you'll notice which one's closest, 6.8, 11.8, or 8.9. And definitely that middle point for the approximation is the best one. So a lot of the stuff that you're going to do is going to take a little bit of paper. It's going to take a little bit of time, but you gotta hang in there with it, because this is giving you the foundation for how the integrals are going to work.